Hello, my name is Raluca Vereshtiuk and I will present the first part of the Enterprise Integration Design Patterns presentation. So let's start. It is uncommon for today's application to live in isolation. Users expect instant access to all functions, which may be provided by different applications and services inside or outside Enterprise. Integrating applications and services remains more difficult than it should be though. Developers have to deal with asynchrony, failures, and incompatible data models. The lack of a common vocabulary and body of knowledge for asynchronous messaging architectures made it difficult to avoid common pitfalls. Enterprise integration is the task of making separate applications work together to produce a unified set of functionality. Some applications may be custom developed in-house, while others are bought from third-party vendors. The applications probably run on multiple computers, which may represent multiple platforms. It may be geographically dispersed. Some of the applications may be run outside of the enterprise by business partners or maybe customers. Other applications may need to be integrated even though they are not designed for integration and cannot be changed. These issues and others like them are what makes application integration difficult. There are various options for connecting applications with one another. One of these options is messaging. Messaging makes applications loosely coupled by communicating asynchronously, which also makes the communication more reliable because the two applications do not have to be running at the same time. Messaging makes the messaging system responsible for transferring data from one application to another, so the applications can also focus on what data they need to share, but not to worry so much about how to share it. Like most technologies, messaging involves certain basic concepts. Once you understand these concepts, you can make sense of the technology even before you understand all of the details about how to use it. We will focus on the concept of transformation. Various applications may not agree on the format for the same conceptual data. The sender formats the message one way, yet the receiver expects it to be formatted another way. To reconcile this, the message must go through an intermediate filter, namely a message translator, that converts the message from one format to another. The message translator is responsible for translating messages between applications. This ensures compatibility between applications that support different data types. Different applications typically use different data types. Therefore, for two applications to successfully communicate, we should translate the messages that pass from one application to the data type compatible with the receiving application. In this case, a translator changes the context of a message from one interface to another interface. This ensures that the message is good for the context rules of the backend service. The message translator is the messaging equivalent of the adapter pattern. An adapter converts the interface of a component into another interface, so it can be used in a different context. This is the same in messaging.
Hello, I am Andreea Ungureanu and I will present the second part of the project. Context example. For instance, in a multi-application context, the accounting system may be more interested in the ID numbers and bank account information, while human resources may be interested in phone numbers and addresses. As a result, the systems expect to receive messages that mimic the application's internal data format. Levels of transformation. Message translation may need to occur at a number of different levels. For example, data elements may share the same name and data types, but may be used in different representations. XML file versus comma-separated values versus fixed-length fields, or all data elements may be represented in an XML format but use different tag names. To summarize the different kinds of translation, we can divide it into multiple layers, loosely borrowing from the OSI reference model. The data structures describes the data at the level of the application domain model. It is therefore also referred to as the application layer. This layer defines the logical entities that the application deals with, such as customer, address, or account. It also defines the relationships between these entities. Can one customer have multiple accounts? Can a customer have multiple addresses? Can customers share an address? Can multiple customers share an account? Is the address part of the account or the customer? This is the domain of entity relationship diagrams and the class diagrams. The data types layer defines the application data types that the application model is based on. Here we deal with decisions whether date fields are represented as strings or as native data structures, whether dates carry a time of day component, or which time zone they are based on. We may also consider whether the field postal code denotes only a US zip code or can contain Canadian postal codes. In case of a US zip code, do we include a zip +4? Is it mandatory? Is it stored in one field or two? Many of these questions are usually addressed in so-called data dictionaries. The issues related to data types go beyond whether a field is of a type string or integer. The data representation layer is also referred to as the syntax layer. This layer defines the representation of data that is transported. This translation is necessary because the transport layer can only transport characters or byte streams. This means that complex data structures have to be converted into a character string. Common formats include XML fixed-length fields or proprietary formats. In many cases, data is also compressed or encrypted, carries check digits or digital certificates. In order to interface systems with different data representations, data may have to be decrypted, uncompressed, and parsed, then the new data format rendered, and possibly compressed and encrypted as well. The transport layer at the bottom of the stack provides data transfer between the different systems. It is responsible for complete and reliable data transfer across different network segments and deals with the lost data packets and other network errors. Transformation is such a common need that there is a defined standard language for the transformation of XML documents. Part of XLS is the XLS transformation language, a rules-based language that translates one XML document into a different format. For example, let's assume we have an incoming XML document and need to pass it to the accounting system. If both systems use XML, the data representation layer is identical and we need to cover any differences in field names, data types, and structure. Let's assume the incoming document looks like this.
The XML document on the left contains customer data. Each customer can be associated with multiple addresses, each of which can contain multiple phone numbers. The XML represents addresses as independent entities so that multiple customers could share an address. Let's assume the accounting system needs the representation in the right. The resulting document has a much more simpler structure. Tag names are different and some fields are merged into a single field. Since there is room for only one address and phone numbers, we need to pick one from the original document based on business rules. You may wonder how this was done. The following XSL program transforms the original document into the desired format. It does so by matching elements of the incoming document and translating them into the desired document format. In a nutshell, the XSL template are called whenever an element in the incoming XML document matches the expression specified in the match attribute. For example, the line XSL template match customer causes the subsequent lines to be executed for each customer element in the source document. The next statements concatenate first and last name and output it inside the name element. Getting the address is a little trickier. The XSL code looks up to the correct instance of the address element and calls the subroutine getAddress. GetAddress extracts the address and phone number from the original address element. It uses the cell phone number if one is present and the home phone number otherwise. Now for the actual coding example of this design pattern, we will be using RabbitMQ, which is already running on my laptop, as you can see here. And we will be using Python and Pika, a library from Python, to create a connection. Firstly, let's have a look on the XML file. Here we have the XML file that was presented in the presentation as well. We have a customer which have two addresses. And as you know, we will want to firstly make this a little smaller, because for some departments, departments won't need so many data. And also we will want to change the language from English to German or Romanian, for example. So here we have the XSL for German, which here, for example, instead of client in English, we will have Kunde, and instead of street, we will have Straße, and telephone. I don't know how to say that. And in Romanian, we have clientul, strada, oraș, număr de telefon, whatever. Then, in the code, we will firstly have to create the connection, which is here the localhost. In cases of bigger projects, there can be the IP here. Then, once we have a connection, we have to connect to the channel, and then from the channel, we have to connect to a queue, because every channel can have a multitude of queues. Then we actually send the message from the producer to the consumer. In our case, we'll be sending this X, which is the actual name of the XML, which will be received from the keyboard. And in the consumer side, we again create a connection, create a channel, and then declare the queues. Here it's the queue. And here it's once it receives a message in that queue, what it should do. So it will be doing this method callback, which is this one. And then this one line, it's what it... so by writing this, you actually say wait for messages or start. Yeah. And the callback function, there are multiple parameters which can be used, but in our case we only care about body. And here we have, for example, here in callback we just call the methods transform to German, transform to Romanian, and it will also print the received message, aka the body. So for transforming to German, it's just using LXML point A3, I think. And it will just parse the XML, then it will, here it will be using, for example, in the Romanian side, the XSL named raw.xsl. Then it will transform the XML into another XML, into a string of bytes, I think, and then it will transform it. And then it will print it. So let's see how it runs. Here we will writing fichier.xml. Okay, and now if we run the consumer as well, it received fichier.xml, and then this is the translation. So if we have a look, we have the clientul with the name Joe Doe. Adrese. Okay, I will have to change more tags because some of them are still in German and some of them are still in English. Okay, whatever. We have strada, oraș, da. It translated mostly because I didn't change all the tags, it seems like. Yeah, but yeah, overall this was it. I will be putting the code written as well. Thank you.